Hello Internet, this is JF, and this is Introduction to Programming in ATS, Chapter 9 and Video 9. There's going to be a lot of reading in this, so let's get to it. Introduction to Dependent Types. The types you've encountered so far in this book are often not adequately precise in capturing program invariants. For example, if we assign the type int to both of integers 0 and 1, then we simply cannot distinguish 0 from 1 at the level of types. This means that 0 and 1 are interchangeable as far as type checking is concerned. And we saw that in a previous video with assigning some or none to a value. In other words, we cannot expect a program error to be caught during type checking if the error is caused by 0 being mistyped as 1. This form of imprecision in types can become a crippling limitation if we ever want to build a type-based specification language that is reasonably expressive for practical use. Do we want to do that? I guess the book is introducing the type-based specification language, but okay. Moving on, enhanced expressiveness for specification. So the primary purpose of introducing dependent types into the type system of ATS is to greatly enhance the expressiveness of types, so they can be employed to capture program invariants with much greater precision. Generally speaking, dependent types are types dependent on values of expressions. For example, bool is a type constructor in ATS that forms a type bool of B when applied to a given Boolean value B. So you have like bool of true, bool of false, or B is a Boolean and B is not false. I don't think like the not equals like this doesn't work. Let's just say it's true. There you go. I think I also use expressions here like bool, like A is greater than B, when you have A and B that are both ints. I think you can do that. We'll see that later on. All right, as this type can only be assigned to a Boolean expression of the value B, is often referred to as a singleton type. That is a type for exactly one value. So yeah, true has the type of bool true, and bool true can be applied to nothing else. Same as false, bool of false. I'm going to go on to say that that's the same for ints. So, 5 is an int of 5, and you can't apply that to anything else. Please note that bool and int are often, they're overloaded as they refer to non-dependent types. So true is also a bool, and 5 is also an int, and it's also an int of 5. So he's going to introduce a bunch of dependent types, and particularly present a flexible means for the program to declare dependent data types. The syntax of ATS is a simply typed language. I don't know what that means. I don't know what a complex type language would be. But moving on, the types in this language are called sorts so as to avoid some potential confusion. So the statics of ATS, they have sorts rather than types. So bool is a sort. Bool int type and t at yp are types. And by the way, the next revision of ATS, ATS 3, this is just going to be called this, and type is going to be tbox. So the thing you usually want is going to be a little bit nicer, and the thing you want sometimes is going to be a little more clear about, it's just box stuff. So the sorts bool and int are classified as predictive sorts, predicative sorts, while the sorts type and t at yp are impredicative. I don't know what that means anyway, so who cares if I pronounce it right. Moving on, a box type is the static term of the sort type, while an unboxed type is a static term of cat. So yeah. As types, bool and int are static terms of the type sort t at yp. Okay, so bool of b and int of I are both unboxed types. Oh, and he gives they're constructors. So it's like fun bool takes a bool, returns a type. Well, you do it like this. So then you apply that function to, like true, or apply that other function to like 42, and then you get a type, which happens to be an int of 42. Okay. So the type constructor list is of this sort. It creates a box type from an unboxed type. There's a variety of built-in static functions in ATS for constructing static terms of the sorts bool and int. So list some. So And the stacks of ATS, you have negation, addition, subtraction, multiplication, division, all this stuff. You also have not equal to, so you really do have that. And also not equal to with the angle brackets. You also have Boolean negation, so true becomes false. We have disjunctions and conjunctions. By combining a sort with one or more predicates, we can define a subset sort. For instance, the following subset sorts are defined in it's the prelude. So actually, not even the prelude. It's not this thing that you styled. So these are already built into the language. So let's try. Okay, we have sort def nat. So nats are ints greater than 0, greater than equal to 0. Pauses are ints that are greater than 0, and negs are ints that are less than 0. Although they're defined like this. So it's not, we couldn't say like extern. Pretty sure you can't say that. Make the static identifier neg is unrecognized. So even though there's a sort there, like there's a sort neg, but it's not a type. But if you were to say it says int of type it's neg, you can say int of in. Yeah. So you can use them in statics, but not in types. You could say type def neg, and then that would be overloading it. Not really overloading it, but like this is a type, and there's also a sort called neg, even though they're grammatically different. Int of, I don't think you can do that. Can you do that? Static identifier neg is unrecognized. No, it doesn't like that. But you can still say int is a neg. I should be able to do this. Yeah. So you can create a type and then use the sort here in order to say that you have an int of that. You were refining an int based on it. Basically, just a shorthand for it's an int that has this it's less than equal to -1 or less than 0. So you can do it either way. But yeah, trying to talk about it like that is a little bit awkward, isn't it? So it's a sort. It gets because you can use it in the statics, but not in the dynamics. And it's not a type. So he gives them a bunch of other sort defs. So a nat4 is you can only apply that to 0, 1, 2, 3, 0, 1, and 2, and 3. And he also says you can have multiple predicates. So you can say nat3 is 0 that's less than or equal to a, or a is greater than or equal to 0, and a is also less than 3, and it gives you 0, 1, and 2. There's some other ways to do it. So you have the or and operators, boolean operators. In order to unleash the expressiveness of dependent types, we need to employ both universal and existential quantification over static variables. For example, the type int with a capital I, is defined as an int. So it's an int of a, where a is some kind of int. And probably neg and pause are also defined. So let's make that fun again and say capital N neg this time. No, it's not. It's pause defined. Well, nat is. I know nat is. I guess it just you don't need. Well, it doesn't think you need pause and neg as much, but nat is in fact defined, and it's the same way as there, same as int. And it's a shorthand way. If you want to have dependent types, but you don't want to say anything about them in particular, you can just say okay, capital I int. That's a convenience for you. So the syntax in square brackets a colon int means existential quantification over static variable a of the sort int. So it says there's a static variable a and it has the sort int. And then you can also list some predicates about it. Essentially, this means that for each value of the type int, that's for the type def we're creating, for each value of this type, there's an integer I that is of the type int of I. Okay. Let's move on. Is it syntax sugar? Like, or I don't think this is like. I think that's more of like you could speak of it as if it were syntax sugar, but really it's just saying there's a static variable a and it has the sort nat. Okay, well nat is defined as a is greater than or equal to 0, but what is it? I don't think you'd call that syntax sugar. That's like saying like function application is syntax sugar of expanding an expression around these variables. So at this point, types have already become much more expressive. For instance, we can assign a type. Before, we could only assign int of int, or int. If we have a function that takes an int and returns an int, we can only give it that type. But if it maps integers to natural numbers, then we can now say, oh, it takes an int and returns a nat, which is much more precise because now looking at the type, it doesn't return any kind of negative numbers. So in order to relate at the level of types, the return value of a function to its argument. Okay. In order to relate at the level of types, the return value of a function to its arguments, we need universal quantification. For instance, the following universally quantified types for a function returns the successor of its integer arguments. Okay, so you introduce so there's a static variable I, has the sort int, and then there's you have a function that takes an int of I and returns an int of I plus 1. So I'm going to define that. Fun suck. There you go. Suck of 5 is 6. And if we were to change this, we no longer type check. Unsolved constraint. Well, you said that I minus 1 is equal to I plus 1. And that's clearly not the case. Good job. So it looked at this and said, okay, n minus 1, that has the type of int of I minus 1. And is that the same thing as I plus 1? No, it's not. That's a type failure. Or a type checking failure. Okay. So again, universal quantification over static variable I, which has the sort int, and the scope of this quantification is the function type following it. So another way to do this is we could say extern fun suck, and it has the same type. I can implement it. And that is the same issue of, if you do it wrong, it's a type failure. And again, like automatically expands. Like I just say that it has the sort nat, and we know what nat means because we have a sort def about it. Let's say we had so as we introduce static variable n, which is of this sort is 5, and then n takes an int of n and returns void. So we're going to call that with something other than 5, unsolved constraint. Line 14, it says, hey, 10 doesn't equal 5. Now it does. So sort def. So like it keeps saying like, oh well, is5. You can think of that as expanding to, expanding to an event n equals 5. But just say it's an is5. That seems fine to me. All right. So here are a bunch of syntax. Here are a bunch of interfaces for commonly used functions and integers. So we've got addition and subtraction, division. We have all of the dependently typed function types of them. So we have I and j of sort int, and then there are two. The syntax with like just a space, it's the same as the syntax with parentheses around it. So instead of like indivi like that, I could just say space. That's the same thing you can do in the language itself. Like if you only have, you can say blah 5. And I can't do it here as I have multiple arguments, but with 5 it's fine. See? So if you add I and j, you get I plus j, I minus j, times, divide. And also, bool cannot, it doesn't have to be just true or false. It can also be an expression, a Boolean expression that values the true or false. So I think you can take something like, let's take two integers, n and a Boolean. Or say greater than. So you have to pass it a Boolean, and that Boolean has to be true if n is greater than m. Okay. Or it could also be false. Okay, I was thinking of doing it right here and say, okay, also n is greater than m, but if I don't do that, then it just has to match the Boolean. So let's say all right, so greater 2, 4, and false. That's will be greater for 2 and true. So that works. So indeed, 2 is less than 4, and 4 is greater than 2. But if I were to change the Boolean and say, okay, actually, this is true, then look at type checks. And type check is, so true has to be equal to the greater than of 2 and 4. So it says, okay, 2 and 4, so 2 greater than 4 returns something that isn't true. And that is the case. Interesting. So these are all defined in integer sats, which is, it's automatically loaded. It's not even in like this include up here, like you get this with an empty ATS file, apparently. And he says, they're also operators that are overloaded with these functions. So it is now a proper moment for me to raise an interesting question. What does a dependently typed interface for the factorial function look like? After seeing some of the above examples, it is only natural for one to expect something along the following line of thought. So you have an I, which is of sort nat, of natural numbers, and you have a function that takes an I, or an integer of sort I. That's not a sort. That's the static variable I, and what we know about I is that it's a nat. So it's not really a sort. It's anyway. You have a function that takes an int of I and returns an int of factorial of I. So factorial here would be a static function that ATS knows about. Okay. The very problem with this solution is the static function like fact cannot be defined in ATS. So the statics of ATS is a simply typed language. Okay, does it explain that? No, but it just says that the statics of ATS does not allow any recursive means. So when you construct static terms, you can't use recursive functions. This design is adopted primarily to ensure that equality and static terms can be decided based on a practical algorithm. So instead of Idris, where a very small program, like a program of this size, will sometimes take like 30 seconds to compile, ATS usually compiles pretty quickly. But that gives you limitations. Like in Idris, if you define a factorial function and if it's a total function, then you can just start using it in your static types. But you can't do that in ATS. So, as type checking involving dependent types essentially turns into verifying whether a set of equalities and built-in predicates and static terms hold, such a design is of vital importance to the goal of supporting practical programming dependent types. In order to assign an interface to the factorial function that precisely matches a definition of the function, we need to employ theorem proving, which is a later chapter. So, you can do a lot with just simple constraints and sorts and stuff like this. But you can't do everything. All right, so constraint solving during type checking. So type checking in ATS involves generating and solving constraints. As an example, the code below implements the well-known factorial function. So yeah, factorial takes an n, if it's a nat, takes x, which is a nat, as we know up here, and it returns a separate nat. So all it's saying is that there are two nats. It doesn't make any kind of relationship between them. It doesn't say they're related to each other at all in any way. Says if x is greater than 0, then x times fact of x minus 1. So yeah, else 1. That's the factorial function. Which means that fact returns a natural number r when applied to the natural number n. When the code is type checked, the following constraints need to be solved. For each natural number, n greater than 0 implies that n minus 1 is greater than or equal to 0. So yeah, in this function call, like in this clause of the if-then-else expression, x minus 1 has to be greater than or equal to 0 because that's an argument to fact, and fact only takes natural numbers. Up here. So yeah, if you were to just say if you just have the fact and define it as something that calls fact without having this x is greater than check, then that would fail constraints. But since you have x is greater than 0, it knows that x has to be at least 1, and it knows that 1 minus 1 is greater than or equal to 0, so that still passes. For each natural number n and each natural number r of 1, what? n greater than 0 implies n times r of 1 is greater than or equal to, I don't know what the syntax is. Well, I'm just saying there's also an implication about the return. So the x times fact of x minus 1 has to return some kind of int of all it's saying that has to be a natural number. So again, if you were to say, let's say else -1, then it would say, okay, well, hold on. What if I pass 1 to this function? Well, that'll give me 1 minus 1 is 0, and then that'll give me the else part of this if-else expression. That'll give me -1. But here it says that the return type has to be a natural number, and -1 isn't a natural number, so that also fail constraints. So yeah, then it applies it. It actually has to be greater than or equal to 0. But for each natural number n, 1 is greater than 0 holds. I didn't follow. I guess that's some implication derived from the second one that I didn't follow. All right, well, the first constraint is to dedicate generated due to the call factorial of x minus 1. Okay, yeah, which requires x minus 1 to be a natural number. The second constraint is generated in order to verify that x times factorial of x minus 1 is a natural number under the assumption that factorial of x minus 1 is a natural number. Okay. The third constraint is generated in order to verify that 1 is a natural number. Okay, so completely separated. Okay, we looked at the if case, and the if case was this whole expression. That has to be a natural number. And it says, okay, look at this else case. What is the else case? That's 1, and is 1 greater than or equal to 0? Yes, it is. Okay. So this third one doesn't have anything to do with the second one. It's just the else part of this if-else expression. All right, so the first and third constraints can be readily solved by the constraint solver in ATS, which is based on the Fourier-Motzin variable elimination method. So that's sometimes called ATS/LF. That's ATS's built-in constraint solver. However, the second constraint cannot be handled by the constraint solver as it's non-linear. The constraint cannot be turned into a linear integer programming program It can't be turned into a linear integer programming problem due to the occurrence of the nonlinear term, n times r, whatever that means. So, yeah. So you have multiplication, apparently, and that's not good. While nonlinear constraints cannot be handled automatically by constraint solver in ATS, the programmer can verify them by constructing proofs in ATS explicitly. That's one method. Another method you can use explicitly for this is to bring in an external solver that is more capable than ATS's built-in solver. All right. By default, the constraint solver implemented for ATS, ATS2, makes use of the standard arithmetic of infinite precision. So that's why when you look at all these errors, it says like intf 4. So for the sake of efficiency, one may choose to use machine-level arithmetic for solving integer constraints. So if you do use that, you can get overflow, but it seems like you never really get overflow, so don't be too concerned about it. But yeah, the default doesn't have overflow. So by default, ATS doesn't have overflow because it uses it, uses GMP for integers in the constraint solver. But if you want to be more efficient, you could use machine integers. All right, so a string in ATS is represented in the same manner as in C. It is a sequence of adjacently stored non-null characters followed by the null character. And its length is the number of non-null characters in the sequence. So if you have a string of 5, then you're actually referring to a memory location that has 6 bytes, but the last one is 0. Conventionally, such strings are often referred to as C-style strings, which are notoriously difficult to be processed safely, as indicated by so many bugs and breaches due to misusing such strings. As a matter of fact, ATS is the first practical programming language that he is aware of that can fully handle C-style strings in a safe manner. In ATS, strings of a type constructor of the sort. So again, string is a type constructor, so it takes an argument. Yep, string takes an argument, and there's an int, string of int. Given a static integer n, string of n is a type for strings of length n. And the string refers to non-dependent types. So there's also a string type, there's a string event type. Or rather, a string that takes an int and returns a type, or a t-box in ATS3 terminology. Okay. So this has typedef string in caps, so that's just a string that's refined by a natural int, a nat. Alright, so the following two functions are commonly used for traversing a given string. So a string is at end, you're saying, am I looking at a null byte? Size, okay. What? Okay, I here is a reference. So, not a reference, it's an index. So you're indexing into the string, and you're saying, is I the same length as the string? Okay, so it's like indexes. So you have a string of 5, and you have indexes. So your indexes are going to be 0, 1, 2, 3, 4. And there's also 5, but that's the index of the null byte. So string is at end. So if you say string is at end, like that, you pass it a string, so some str. And let's say 5. Let's say this is a string of 5. Then this would be true, because your index is the same as the length of the string, which means you're looking at the null byte. Okay. If it were 0 or any other number, like 0 between 0 to 4, that'd be false. Then we have string is not at end, which says, okay, I is less than n. So again, if it's 0 or through 4, given a string of 5, it's going to be true there. Yeah. Obviously, either one of the following can be implemented based on the other. So an example, the following function computes the length of a given string. All right, let's just go ahead and do this. So found string length. We have n that's nat, and we have a string of n and we want to return a size t of n. Okay, sure. So again, like if you pass a string of 5, it's expecting 5 to be the answer. So size t of 5 to be the answer. Yeah, I was gonna point out that like in Idris, like you can do stuff like just say, oh, the answer's n, and like magically pull this out, but you can't do that in ATS because at runtime these types and sorts and refinements don't exist. All right, so it says this is passing a str, and you're passing a size t of 0. So the first index. Again, I is not. Okay. So it's borrowing the static variable from the function it's in. And n minus I. This is your termination metric. So as long as n minus I goes down on every recursive call, then it's ATS says, okay, well this is going to terminate eventually. So like n minus I, whatever that is, the next time the loop recurs, this has to be something less. So since I is going up, n minus, so n is 5, then it's going to start out n minus I equals 5, then n minus 1 equals 4, n minus 3 equals 2, and so on. So that works. Star string of n, I size t of I. Is not at end. So if it's at end, then just return I. That seems like it makes sense. Parsing error. Where is the parsing error? It's line 25. 25, oh. Okay, what's that? Dynamic expression cannot be assigned to some gint, whatever. It's on line 21. So if string is not at end, stir I, then loop stir suck of I. Oh, it's probably because I have suck defined right here as taking ints, and in fact, this is all size t's. Yeah, that's the issue. So it's really okay. Yeah. So the actual term is an unsigned int that's of kind size. So at type size, so size t, and the needed term is at type int size int, or just and at type int, which is int. So yeah, it's a little bit hard to read. All right, so the function loop. The function loop in the body of a string length is defined tail recursively, which can then be translated into a genuine loop in the generated C code. So yeah, although this implementation of string length looks fairly plain right now, is actually an exciting achievement in the pursuit of practical programming with dependent types. So I guess historically, like, this is a really cool thing. So I think it's fine. Two functions for accessing and updating characters stored strings. So I've got a type def here, char and z, which is it's a character that's not 0. So you have string get at, it returns a char and z, overloading that. So yeah, your usual bracket notation for accessing arrays, and also works with strings, and this is how those are defined. with the interfaces for them. The type constructor chars of the sort takes a char and returns an unboxed type, which makes a static character C to form a singleton type char of C. So yeah, singleton type again meaning that if you have a char of something like char of the f, then it only refers to one thing, which is f itself. Thus, the type char and Z is for all non-null characters. The following define function string find traverses a string from left to right to check whether a given character occurs in the string. Okay. So string find takes size LT. So yeah, this is just it's a size T refined by a natural number being less than an int. So I guess this would have to be an int actually, because it can't be a negative number in order for I to still be a natural number. So we have an option. So the character may not appear in the string. That's interesting. It's a local type def. I also like how this local type def is using a static variable in, which is defined right from the outer function. This looks pretty straightforward. The only thing I would point out is that when you're constructing sum of I, he gives an explicit type. There is some inherent inefficiency in the lookup in the implementation of string find. A given position I is first checked to see if it is strictly less than the length of the string stir by calling string is not end, and if it is, the character stored at the position of the string is fetched by calling string get at. These two separate function calls are merged into one in the following implementation. So here it's saying, let's first check and see if we're at the end of the string, and if we're not, then check the thing at the string at that point. But the string is not end, like that. So you're doing the same memory fetch twice, and you're just throwing away the result here. So this one I imagine does the memory fetch and then says, hey, is that 0? Yeah, which is exactly what it does. But what is string test at? It explains. What the hell? Okay, so string test at returns a character which is not null if the index is less than the size of the string. And it is null if the index is greater than or equal to the size of the string. So that's fascinating. By checking the return value of a call to string test at, we can readily tell whether the position I is at the end of the string stir. So yeah, this level of complexity in dependent types is something I hadn't even seen prior to this. Handling strings safely and efficiently is a complicated matter. It's a complicated matter in programming language design, and a great deal of information about a programming language can often be revealed by simply studying its treatment of strings. Okay, so an ATS properly processing C-cell strings also makes essential use of linear types, which we cover later on. Really, again, I'm not sure what strings have to do with linear types, unless you're dealing with linear strings, which is actually I guess that is quite important for a memory use position. So here's an example of binary search on arrays, which I'm going to kind of go through. I don't see anything real special here. Okay, so it says this is a convincing example if you don't really believe in dependent types. But I assume if you're watching this video at all, if you started this series, then you kind of do believe in dependent types. So just go on. Termination checking for recursive functions. So there's a mechanism in ATS that allows the programmer to supply termination metrics for checking whether recursively defined functions are terminating. So again, I've mentioned Idris a few times. It has a termination checker, but I think it's built in. Like it just does it, and you don't really have control over it. The same way that Rust has a borrow checker, and it just does it, and you don't have any control over it. Like you can turn it off with unsafe, and do stuff, but you can't you can't like work with it. Whereas in ATS, most of the features of ATS are things that are exposed to the program or are things you can work with. So it has a theorem proving language instead of a theorem prover that just ascends from the heavens and manages things for you, or descends from the heavens. It will soon become clear that this mechanism of termination checking plays a fundamental role in the design of ATS-LF, the theorem-proving subsystem of ATS, where proofs are constructed as total functional programs. So your proofs have to be total programs, which means they have to terminate, so you have to prove that they terminate. A termination metric is just a tuple of natural numbers, and the standard lexicographic ordering of natural numbers is used to order such tuples. Why do I care how they're ordered? In the following example, a signal metric n is used to verify that the recursive function of fact is terminating, where n is the value of the integer argument of fact. Okay, so it's taking the static variables that you defined elsewhere and you reuse them in your termination metric. So yeah, n it's that, and the termination metric uses that same n. So note that the metric attached to the recursive call fact of x minus 1 is n minus 1. Okay, so when you on recursive calls, that's where you consider the metric. So factorial of x minus 1. Okay, let's look at this n minus 1 metric. Okay. So I guess I was wrong. Before I said it has to be less. Apparently it has to be like, it's strictly less, like 1, it has to be 1 minus the previous value. Okay. So essentially, termination checking in ATS verifies the metric attached to each recursive call in the body of a function is strictly less than the initial metric attached to the function. So fact starts with n, and then on every recursive call, it has to be n minus 1, then the previous value minus 1, the previous value minus 1. So it shows how max of 101 minus I comma 0 will eventually get you down. Because you start at like 101, or what was I? I is an int? Okay, so, but I could be negative then. I don't know what this particular function is, but yeah, this is again a very complex return type. But it's a simply typed language, she says. The metrics applied to verify the termination of F91 is max 101 minus a comma 0, where I is the value of the integer argument of F91. So you get the maximum. So if this goes negative, then it's just 0. It suggests that you manually verify that. I am not going to. As another example, the following code implements Ackermann's function, which is well known for being recursive but not primitive recursive. So you can't make a tail recursive, I think that's what he means. Because you have an acr call that includes an acr call. So like there's a recursive, there are two recursive calls that are in, one of them is embedded in the other. On the if case, and then on the else case, you just have our simple recursive call. All right, the metrics applied for verifying the termination of acr is a pair m comma n. So m and n are the values of the two integer arguments of acr. Okay, well yeah, again, static variables, we're using them here. The metric is attached to three recursive. So there are three recursive calls, and the metrics attached to them are from left to right: m minus 1 comma k, m, and then n minus 1, and then m minus 1 comma 1. What? Okay, so the metric of this call right here on the else branch, it's always m minus 1 comma 1. So m, what? The metric over here, this one is always m comma m minus 1. And I guess this evaluates to k, so it says, okay, there's also m minus 1 comma k. Well, whatever. It says clearly these metrics are all strictly less than the initial metric m comma n, according to the ordering. Termination checking for mutually recursive functions is similar. In the following example, is even and is odd are defined mutually recursively. So we've got fun, is even, and is odd, and their termination metric is 2 times n and 2 times n plus 1. So because the termination metric of is even n is 2 times n, which follows. That's what it says right here. And the termination metric of 2 times n is you pass it n minus 1. So Yeah, I guess that works. So the metrics applied for verifying the termination of is even and is odd are, so respectively. Clearly the metrics n, 0 and n, 1 are supplied for is even as odd. The termination of these two functions can be verified. So if you start with just give it an explicit call, like call is even with 5, and then if you walk through it, you'll see that those termination metrics are satisfied. So an example of dependent types for debugging. So given an integer x is greater than 0, the integer square root of x is the greatest integer satisfying I times I is less than or equal to x. As an implementation of the integer square root function, so here it is, fun I square root. And this implementation passes type checking, but seems to be looping forever when tested. Okay. So this is a buggy function, essentially. So fun I square root, taking int. We're not using dependent types here, so I'm going to implement it exactly as he has here. It says an internal function search, takes an int, an int, an int. Val diff, it's right when it's left. And this is another if case, so we're just going to do that. Okay, then let's move this over a little bit. Alright, so we're defining a function search, and we're using that in search x0x. So this should run forever. Keyword n is needed. Huh? So what? I got some simple syntax error. Line 26, 27, keyword n is needed. 27. So that works. So there's a syntax error in here. I don't think that's the case. It doesn't like that. Now, I'm really not seeing the syntax error. $32. Oh, that's the syntax error. Okay. Yeah. I had equals where I needed a fat arrow. And now I need to get rid of this. Great. So that compiles, that type checks, and now we have an infinite loop. Instead of going to the standard routine of debugging, i.e. Inserting calls to some printing functions, let's attempt to identify the cause for infinite looping by proving the termination of the function search through the use of dependent types. Okay. So right now we just have int and int, so this isn't helpful. We have no static variables that we can put in a termination metric. However, the program may have thought that the function search should possess the following invariants. So L times L is probably less than or equal to x, and x is less than or equal to r times r. Now we're also expecting r1 minus l1 to be less than r minus l. All right. Okay, so instead of capturing this first invariant, we're going to capture the second invariant because ATS can't express the first one neatly. So I'm going to change the type of the search function. So now we have search of x of net and 3 more. Okay, L and R, then also nats, and L is less than R. And then we have a termination metric of R minus L. And this, see, even though I have only 4 tabs of 4 spaces, this is still way too much. It just goes right off the end of the screen. This is, in fact, yeah. Well, it's only 80 columns. But we can start doing nat. You can start use type defs and sort defs to abbreviate these somewhat. Anyway, so the termination metric is now R minus L. And we have int of x, int of L, and int of R. Then we get all kinds of, no, it's a type failure. Oh, I see. Introducing the nat one above here, or the one for x above here. Do I have to repeat the static variable? All right, unsolved constraint. We have L plus something is something, yeah. Yeah, whatever. L plus something is not 0. There's a constraint failure on line 36. They're all the same. What? It is now rather clear that infinite looping in the previous implementation of search may happen if search XLR is called in a situation where R minus L equals L, as potentially lead to a call to search of the same arguments. So R minus 1 equals L. All right, I'm sorry, that's not clear to me. Anyway, being precise and being able to enforce precision effectively, the program will surely notice his or her need for runtime debugging is diminished rapidly. So I think this is probably a bad example because I didn't really go through it and understand exactly what he's doing. But the point is, if you thought about your program, okay, I know it should have these invariants, then you can put those invariants in your program, and then the constraint checker will help you out. It's like, oh, actually, you're totally failing. All this is true. The termination metric is no longer true, and so on. And that can help you just by putting the constraints, putting the invariants you think it has into ATS. Then ATS can help you ensure that they actually hold, and that way you can solve bugs. So you can see, okay, where exactly is like I said, what is it? Line 36, offset 12. So yeah, there's a constraint failure right here somehow. All right, that's not great, but that's the video.